Now in section 4.3, what we're going to do is take a deeper look at our least squares regression line and really analyze a few things that are above and beyond the usual. The first thing we want to look at is the coefficient of determination. We want to know how to compute it and how to interpret it. All right. So the problem is that when we want to know if two variables are correlated, what we're really asking is more complicated than that. What we want to know is, hey, is the variability that I see in this one score, this one value, somehow associated with the variability that I see in this other variable? In other words, when this first variable goes up, that up and downness of that first variable, is that explaining why I have up and downness in my second variable? So the coefficient of determination is going to be a number that tells us how much of the variance in the scores of one variable can be understood or explained by the scores of a second variable. All right, suppose we took the heights and weights of 10 random people, and we expect the heights to vary, i.e. some people are taller, some are shorter. So I'm going to have a circle over here that says, the total variation in height that I see, the up and downness amongst people's heights. And then I have another circle that shows the total variability in weight, right? So some people weigh more, some people weigh less, etc. Now, if there was no relation at all between the two variables, then their variations would not overlap, right? The variability in one thing, like if I'm higher, taller, then that has no relation whatsoever to how much I weigh, right? And that would lead you to a correlation coefficient of 0, and therefore R squared would also be 0, right? Because they're not related to each other. So is that a realistic depiction of, whoops, I just pressed Control N, of height and weight? The answer is no, right? People that are taller tend to be heavier. In other words, here, let me put it this way. There is a relationship between height and weight, i.e., right? People that are taller tend to be heavier. People that are shorter tend to be lighter. That's why when you go to the doctor's office, they have a height and weight chart. I mean, when you go online to a BMI, body mass index calculator, one of the first things they ask you is your height, right? Because it matters. All right. If the two variables are related or correlated, then there should be some kind of overlap or shared variation between them, right? So consider the graphs below. Here's graph 1, right? I have 30% as my R, excuse me. I'm sorry, that was wrong. 0.30 is my R. And so then R squared is 0.09, because 0.30 times 0.30 is 0.09. And you can see there's that overlap in there, right? This one down here, I have 0.30 in the overlap, right? R squared is 0.30, and that's how much variation they have in common, right? And then there are other things that are at play. Right? So, for example, your weight gets affected by things other than your height, and that's why you're seeing all this bit that's outside of the height overlap portion. All right, so what's our explanatory variable? That's height, which was x. What's the response variable? That was weight, as in y. Okay, which of these two graphs depicts a stronger correlation? Well, there's no question about it. It's graph 2. Ooh, if I could spell. Graph 2. There's a larger overlap in graph 2, and R squared and R are higher values in graph 2. So which of these depicts more shared variation? Graph 2, right? So I could say stronger correlation. Here, let me put it this way. For this one, R is higher, right? The R value is 0.55. This one, the R value is only 0.30. For here, the shared variation is larger there because R squared is higher, right? That's what R squared is, the overlap in there. All right, hold on. Okay, just wanted to change that spacing there. Okay, so the stronger the correlation, i.e. relation, the larger the amount of shared variation, right? And that's the overlap in between them. And that means the higher the coefficient of determination, or larger, I guess you could say, larger, the coefficient of determination. All right. Now, what percentage of the total area of graph 1 is in that overlap region? Well, I already mentioned it, but it's 9%. So if you look here, that's what this r squared value is telling you. So let me 9%. For the second one, it's I think 30. Let me double check that. So graph 2, it's 0.30. So 0.30. So that would be 30%. Cool. So which of those is more likely to be an accurate depiction of the shared variation for height and weight? It's a judgment call, but I would say probably graph 2, because height really has a great or a very strong relationship with weight. Though obviously there are other variables that play it well, like exercise and diet and all that good stuff. All right. So that's what the coefficient of determination is going to measure for us. The coefficient of determination is kind of getting at these ideas. It's the amount of shared variation. It's the amount that's in the overlap. So what that means is it's the percentage of variation in the response variable that is explained by your least squares regression line. All right, and by all means, that's the kind of this particular phrase. I would just put that right on your note sheets, right? Because nobody ever remembers it, but that's how to interpret the coefficient of determination. All right, so why does that say least squares regression line rather than each variable individually? Remember, I talked about way back up here that it was the amount of variance that can be explained by the second variable. Well, I don't want to get into it too much, but for our purposes, let's just say that because the line takes into account both of the variables separately, right? So if you really wanted to say, you know, because of the other variable, it's not, or not because of, but explained by the other variable, that's fine. All right, does a high coefficient of determination imply a causal relationship between the explanatory variable and response variable? No, right? No. Again, high correlation or coefficient of determination implies that there is a strong correlation. But that does not mean that there was a cause and effect relationship. Remember, correlation is not causation, right? Because causation requires, you know, experimentation and a whole lot of other things. I don't know what I was going to say. Correlation is not causation because, how about this? Because of lurking variables. I can spell. The only way to eliminate or reduce the effects of lurking variables is experiments, double blind, and all that good stuff. And even then, it's never perfect. Right? So that's, if you get into science, you spend a lot of time trying to make it so your experiment's just right. You have proper controls is what they're talking about. So that, you know, this has to be a properly controlled study with, you know, randomization and stuff. Well, what they're trying to get at is they're trying to eliminate a lot of lurking variables through randomizing which subject gets put into what and all of that. They're trying to make it so that they have eliminated or reduced the effects of lurking variables. But it's never perfect. That's one of the problems with scientific experimentation. It's just really hard to do appropriately. Okay, so how do we use that coefficient of determination for a problem? So here's the fertility rates in 1962 again with the life expectancy. It's a little bit of a lie here. How could you compute the coefficient of determination? It's right there. I gave it to you. So Excel gives you the coefficient of determination. It's right there. So note, if you want the correlation coefficient, take the square root of r squared. Okay. Oops, I guess I should say is given in the graph. No computing necessary. All right. Now, how do we interpret that? Well, 58.03% of the variability in life expectancy between countries in 1962 is explained by our linear regression model. By the linear regression model, or the least squares regression model, or whatever you want to say. Which means, of course, you've got some up and down. Like you've got wealthy countries here and some of them are lower, and you've got poor countries here and some of them have low life expectancy and some of them have high life expectancy, right? Why do you see so much variability? Well, 58% of it is explained by that model, but that means like 42% or so is happening for reasons that the model's not accounting for. There. That means that 41.97, I'm doing that by subtracting it from 1, right? Because 100%. So 41.97% of that variability is unexplained. It's happening for reasons that are out of our control or not accounted for by our model, right? Happening for reasons not accounted for by our model. All right. What about the math scores? So the coefficient of determination, we already found it. Let me put it up here, right here. So we actually already found the coefficient of determination. It's right there in your Excel output, right there. And it's also right here. See it right there, r squared. So let me highlight it and give it a color. And actually, I'm going to say that this was examples 2 and I'm just going to be lazy. 4.2 example 2, 4.3 example 3. Wasn't this 3? Yeah. That way I can be lazy because I don't need to do this all again. All right, so it's right there. Now for finding r squared with Excel, all you have to do really is, if you found r, remember r we found with correlation. So we said, okay, take the correlation and for those two variables. You have to type in the arrays and stuff. We already learned that in a previous one. Then you go r squared, and I just type equals that value, caret 2, enter. Oh, and to move that stuff, all I did was like Control X and then kind of paste it down, right? It's not, Control X to cut it and paste it. So in case you're wondering how I did that so fast. So there you go. Let me make it purple, that way it matches my other one. So StatCrunch finds it and Excel finds it here in the graph real simply, and then you can find it over here just by squaring your r. Alrighty, so it's what was it? Oops, I better write it down. R squared is 0.473. There we go. Now what does that mean? Well, 47.31% of the variability in passing rates, or math test passing rates, I should say. Math test passing rates from school to school is explained by the linear regression model. And that means like 50-some% of it, we don't know, well, it's unexplained by this model, right? It could be happening for reasons that are well known, but it's not accounted for by this model. All right, we're done with coefficient of determination. I'll meet you back here for residual analysis and residual plots.